true. I assumed
Actually,
you
I'm
were.
well, actually, shut up.
Hang on. Please keep the language so I don't have to edit the YouTube. Thank you. The YouTube. The YouTube.
You know, like, have you seen a SpongeBob episode where he makes a circle by like drawing?
Yeah, he draws a head and then he erases all the more detailed features.
It's pretty funny.
No.
That's not bad, actually.
I'm a quitter.
Okay, I'll take it.
Good?
Good. Very good. Thank you. I wish I had a different color. I'm not sure I do. Okay.
Good thing that was recorded.
I'm glad. Do I have a different color marker? No.
Okay, go to Harris Teeter and they sell a big pack of expo markers for like $1.
I do need to. Okay. Now, all right. What I said last time was when you make a triangle, if this circle has a radius, how big is this radius?
1.
1 unit, whatever it is. And from the radius, you can drop down a line and make a right triangle. When you do that, you create, this is a radius of 1. You create this height being y, this length being x. X is equal to your cosine of your angle theta. Y is the same thing as the sine of that angle theta. Now for some interesting examples. What we do now is we take this radius and we spin it all the way around the unit circle and we create triangles. And each of these triangles has the trig ratios you've been used to since the 9th grade. No, or 10th grade, whenever you did it in geometry. When you looked at triangles in geometry last year, orientation did not matter. Okay? If I drew this triangle here with this angle theta, it had a sine and a cosine based on the opposite over the hypotenuse. And if I drew this angle here, this triangle here, and I told you that they were congruent, even though they're not in my drawing, then you would expect this opposite over this hypotenuse to be the same as this opposite over this hypotenuse, as long as you were told the sides were congruent. The fact that one was facing the other way did not matter, had no bearing on the situation whatsoever. Now that we've put this on the Cartesian coordinate plane, though, the whole point of the Cartesian coordinate plane is orientation, which is a fancy way of saying which way are you facing? Where are you looking? Okay? What direction are you headed in or moving in or looking in? So the fact that x is negative over here is about to matter. The fact that y is negative down here is about to matter. And these two triangles, if I put them on the unit circle, will not exactly have the same trigonometric ratios. Yes?
Is that something Rene Descartes thought of when he was high?
I don't think he got this far. I think the trigonometry was added to it later. But the whole idea of positive x, negative x. Yeah, and also Rene Descartes, I'm not sure if he ever got past quadrant 1. Negative numbers were very controversial in 1637. There was a big debate about what they might be used for.
The devil.
That was one of the considerations, actually. Heaven was positive, hell was negative. I don't know. But seriously, but Rene Descartes did almost all of his work in quadrant 1. That's why he would disagree with modern ideas of what some inverse functions are. Because some things that I said weren't inverse functions are if you stick to quadrant 1. Anyway, more of an answer than you probably wanted. So, for example, if I say theta equals 120 degrees, or, what 120, it's twice 60, so that would be 2 pi over 3. See, pi over 3 is 60 degrees. I doubled it, same as 120. All right, what would the 6 trig ratios, we're going back to Monday now where I told you about secant, cosecant, and cotangent, of 2 pi over 3 b. Okay, first we have to draw it on the circle. Where is 120 degrees? I spin the radius that far on the circle. Where do I wind up? Kara's pointing. Do you remember a quadrant number?
It's in quadrant 2.
It's in quadrant 2. Kara's visual, Amy's verbal. We got it. We're here. Okay? 120 degrees goes up to 90 and then keeps going how far? 30 more. Goes to 90, then 120 only goes 30 more. That is not 30, but please pretend with me. Now, I wrote up here, use the reference angle. Here's what that means. I drop this line down and make my triangle. For 120 degrees of standard angle, what reference angle do I have?
60.
60, because I always draw the reference angle in to the x-axis, closer to the closest part of the x-axis from the tip of the radius. Okay? Now, this x length here, is it positive or negative? Negative. Somebody had confidence. If you go to the left on the Cartesian coordinate plane, x is negative. If you go up on the Cartesian coordinate plane, what is y?
Positive.
Positive. Thank you, Saul. Right. So we have y being positive. Here's where we have to go back to this part, where x is the same as cosine and y is the same as sine. Okay, so 2 pi over 3 creates a reference angle of 60 degrees. So to find the sine, cosine, tangent, cosecant, secant, and cotangent of 120 degrees, I use this triangle over here in quadrant 2 with this 60-degree angle. Okay? But I have to keep track of sine, S-I-G-N. Sine matters now. So basically what I've got is the sine of 2 pi over 3 is going to be a negative opposite divided by a positive hypotenuse. The radius is always positive. The opposite and adjacent can now be negative or positive.
Why minus opposite?
Well, because, I'm sorry, I apologize. It should not be minus opposite. It should be positive opposite. Okay, because the opposite is the y. So that's positive. I just wrote that. I don't want to make this more confusing. The adjacent is the x. Thank you. Thank you, Marissa, for catching that quickly. Now, what would the sine of 60 degrees be?
180.
What would the sine of 60 degrees be? Up here next to pi over 3. That. What is it?
Square root of 3 over 2.
Square root of 3 over 2. So that's the square root of 3 over 2. So the sine of 120 degrees is the same as the sine of 60 degrees. Now the cosine of 2 pi over 3, this is what I was just thinking of. In this case, because the adjacent side is along the x-axis and going to the